The differential equation y double prime plus 9y equals 0 has a solution y1 equals the sine of 3x. We're going to use the reduction of order process to find a second solution y2 of x. The process supposes that y2 has the form u times y1, where u and y1 are both functions of x. In this case, y2 is equal to u times the sine of 3x. It's important to remember that u is a function of x. Therefore, when we find y2 prime, we're using the product rule. We're going to write u prime times the sine of 3x plus 3u times the cosine of 3x. You can confirm that y2 double prime is equal to u double prime times the sine of 3x plus 6u prime times the cosine of 3x minus 9u times the sine of 3x. Substituting our expression for y2 double prime in place of y double prime and our expression for y2 in place of y gives u double prime sine of 3x plus 6u prime cosine of 3x minus 9u sine of 3x plus 9u sine of 3x equals 0. And you'll note that every term that has just a plain u, not a u prime or u double prime, is going to subtract out. Now we're going to make our reduction of order substitution. Let w equal u prime. Then we have w prime times the sine of 3x plus 6w times the cosine of 3x is equal to 0. Now to be a little bit formal here, remember that w is a function of x, therefore w prime is actually dw dx. And then we have that times the sine of 3x plus 6 times w cosine of 3x is equal to 0. And this is now a separable equation. We can multiply by dx, divide by the sine of 3x, and divide by w. We end up with dw over w plus 6 times the cosine of 3x over the sine of 3x, that's the cotangent of 3x, dx is equal to 0. Integrating dw over w is going to give us the natural log of w. Yeah, there should be an absolute value, but I addressed that in the previous video, so I'm not going to bother with it right now. Plus, you can verify 2 times the natural log of the absolute value of the sine of 3x is equal to a constant. You may ask, why the absolute value for sine of 3x? I suppose to be formal, but it's not actually going to matter because we're going to take this 2 and put it as an exponent on the sine function, and then it won't matter if it had been positive or negative to begin with. On the left-hand side, we have natural log of w times the sine squared of 3x. And on the right-hand side, we have this constant c, and this is going to cause, I don't know, we're going to exponentiate both sides. And so it's just going to be e to the constant anyway. I don't like this right now, so I'm actually going to take these out and change them. On the left-hand side, we have natural log, natural log. On the right-hand side, why don't we just call the constant the natural log of some c? And so then we again have the natural log of some c. We can do that because c is a constant. Natural log of c is a constant. It doesn't matter what the constant looks like. Now exponentiating both sides is going to give us w times the sine squared of 3x is equal to c. And you can see how nicely that turned out. And then isolating w is going to give us the w is equal to c times the cosecant squared of 3x. Now remember, we had said that w is equal to u prime, therefore u is equal to the integral of c times the cosecant squared of 3x dx. And again, from my previous video, what's going to be the fate of c? It's going to get rolled up into the constants that we write down when we use the superposition principle. I've got good news for you too. Here we have cosine squared of 3x dx in an integral. We should have a u equals 3x, so du equals 3 dx, and so we would multiply and divide by 3, right? You know what's going to happen with that dividing by 3? It's going to get rolled up into that c, which is going to get rolled up into the c2 in the general solution. I'll put all that together in just a bit. I guess I'll be a little formal. Okay, look. I guess for now I'll just do the formal thing and say u is equal then to c over 3 times the cotangent of 3x. I'll be even more formal and say plus d, call it a constant of integration. It's all going to disappear because check this out. We said y2 was equal to this u times y1, right? So in this case, that means it's c over 3 cotangent of 3x plus d. By the way, you'll never see me doing it this way again. Times y1, if we look back at the beginning, the y1 was sine of 3x. So we have that c over 3 cotangent of 3x plus d times the sine of 3x. When we distribute this, we get c over 3 cotangent of 3x times sine of 3x is going to give us a cosine of 3x. And then if we said plus d times the sine of 3x, we're actually now repeating information that we already have. We don't need it. Remember that the general solution looks like y equals c1y1 plus c2y2. And our general solution here is going to be c1, now y1 was given to be the sine of 3x, plus c2 y2. y2 has this coefficient here, c over 3. We don't need it. That's wrapped up in this c2 right here. So we have c2 times the cosine of 3x. We should write down plus d sine of 3x, but we've already accounted for the fact that sine of 3x is part of the solution. Therefore, just as with an integrating factor, we don't need to include this d constant of integration. Furthermore, we don't need to deal with the constants that came from integrating or the natural log of c, all that stuff. When we're doing this process for a homogeneous equation, so it'll change later. When we're doing this process for a homogeneous equation, when we get to this part where we say u is equal to this integral, all we really care about is what's the function that we integrate to, because all the constants are going to get rolled up into what we already have in our final solution. Now I've packaged this as the general solution, but if we go back and look at the instructions here, we were asked for just a second solution y2 of x. See, we were told y1 is the sine of 3x. So we're going to write down here that y2 of x is equal to just the cosine of 3x, the new thing that we found through this process. In contrast to that process, I'm now going to use the formula. Our differential equation is 6y double prime plus y prime minus y equals 0. y1 is given to be e to the x over 3. The formula says y2 is equal to y1 times the integral of e to the negative integral p of x dx divided by y1 squared dx. Therefore, we need, let's see. First of all, we need to identify p. For this to work, our equation has to be in standard form. We do not have a p in front of us yet. So standard form is going to be y double prime plus 1/6 y prime minus 1/6 y is equal to 0, giving us p is equal to 1/6. Therefore, e to the negative integral p of x dx is e to the negative 1/6 x. Putting that into a fraction and that into an integral, we write the integral of e to the negative 1/6 x divided by, now, y1 squared. So divided by e to the 2x over 3 dx. Simplifying the exponential expression, we have the integral of e to the negative 5x over 6 dx. And so y2 is equal to y1, which is e to the x over 3, times that integral, which Okay, technically is negative 6 over 5 e to the negative 5x over 6, which then gives us a negative 6 over 5 e to the negative x over 2. But again, we don't need that negative 6 over 5 because were we to put this together as a general solution, we'd write y equals c1 e to the x over 3 for what we first had, plus c2 e to the negative x over 2 for what we just found, and that negative 6 over 5 is rolled into that c2, therefore we don't need it. Strip all that away. We'll give the second solution y2 is equal to e to the negative x over 2 because that's what the instructions asked us for.